Okay, let's really start with. Uh, we are continuing with. I think you don't have any doubt, and let will continue. Uh, Yesterday we are discussing about the circuit design. Particularly, we are talking about the MOS design, MOS circuit design, MOS circuit design. Let me change the color. In the MOS circuit design, we discussed about the uh, NMOS, uh, NMOS uh, passive load, inverter, and also we discuss about the NMOS active load inverter. Okay, so just a minute. Hello. So let's continue. Uh, so we are discussing about NMOS passive load inverter and NMOS active load inverter. So similarly, we can have a circuit topology for the PMOS passive and PMOS passive and PMOS active load. PMOS passive and active load. active load inverter. Okay, so here that topology is that here topology will be like this. PMOS, you will have a VDD and you will have a ground, and you can have your say PMOS circuit is like this. So you will get your input, and you can get your registers like this, and you can take load here as a output. Okay, so what will happen here, like normally when it is a if you have a logic 1, if it is a logic 1, so PMOS generally is a off, right? If you the here NMOS and PMOS we are taking as a switch. So if input is 1, then MOSFET PMOS will go to the off. So output will be tied to the ground. Output will be tied to the ground. So output you will get as a 0. And when input is a 1, so PMOS sorry, when input is a 0, then output this PMOS will be on, normally on. So now the output will be tied to the VDD, and that will give the logic of 1. So this way, here the load is connected to these registers. So this is a passive load. It is connected. So this is the logic principle. The digital logic. It acts like an inverter. Input is 1, so output will get 0, and input is 0, then output will get 1. So this is circuit topology for the PMOS passive load inverter. So if you replace with the if you replace this passive resistor with the active PMOS active register by using the PMOS device, another PMOS device. So you can have your the topology like this. Topology like this. You have a VDD, and you will have a ground, and you will see that you can have a similarly PMOS, and here the PMOS gate and source will be sorted, and which will connected to the ground, and this is your input, and this is your output. Okay, the circuit principle is like this, that if you give that test vector that is a 0, then it is a okay. So since it is grounded, so normally it is a normally on, and you will get a registers. So if it is a 1, sorry, it is a 0, no, sorry, take it is a 1 like that, same style. So if it is a 1, then it is a off, right? And since this is normally on, the driver active register is on, normally on, because gate and source is connected. So it is on, so output will be connected to the ground, so you will get a logic 0. And when it is a 1, if you when you give the input as a 0, then output this transistor will be on, the driver transistor will be on, so it will try to the this output will try to the VDD, so you will get a logic 1. So this is the circuit topology for the PMOS active load inverter. Okay.
Hello.
So Hello.
Hello, sir.
हाँ.
Sir, I'm saying that
तुम्हारा आवाज नहीं आ रहा है. हेलो.
sir now. Hello.
हेलो. हेलो. हाँ.
Sir, am I audible?
हाँ. Yes. Now it is audible.
Sir, I'm saying that for both passive and active load, we are having same topology here.
Which one you are telling?
So this for PMOS inverter.
हाँ.
Sir, then what's the difference between both?
Okay. This active load and passive load.
Yes, sir.
No. See. One is a passive load. Passive. Do you know what is a passive load and active load? Passive resistor and active load.
Yes, sir.
Sorry, passive resistor and active resistor. See, okay. So see here it is the register. It is register is realized using your passive component. Means you are realizing your register by designing a register or some dedicated register, and or you are realizing on the silicon with a particular material, right? But in this case, in this active load case, that PMOS device, okay, the PMOS device is used as a active register. Active register. Okay, this is this PMOS device is used as a active register. Let me tell you before going to that, I think what you have a doubt. I will come to this realizations. Say, for example, take a passive register. Okay, let me clear your doubt. Say, take a passive register. How you can realize on the silicon? Okay, how you can take a register, passive register? How you realize in the silicon? So take any resistive material, silicon material, and you will get your terminal say A, and this side you will get your terminal B. Okay, B. So since this is a resistive material, okay, that depends upon the conductivity or resistivity. You can say that it will you will get a resistance equal to rho L by A, right? L is a length of the resistor and A is a cross sectional of your resistors. Okay, cross sectional of your. If you take this one like this, so so suppose this is your area A, cross sectional area A. So small a, I will take it because node I have taken A and B. So since this is L, so the total resistance you will get it R into rho into L by A, which one you know, right? From the circuit point of view, like from the physics, that R equal to rho into LA, where rho is your resistivity. Okay, rho is your resistivity. So here the what you will get the resistance, you can realize it that see, resistivity is a constant for particular material, right? Which particular material you will use it, resistivity is a constant. And what next is available to you, that to get a desired resistance, so you can have a particular length, you have particular length of a resistor, that metal layer or that silicon layer, and you will get a particular cross sectional area. If you increase the length of your this silicon layer, then the resistance will be increased, right? Or if you decrease your length, then I means R is proportional to L and inversely proportional to the 1 by A. So by varying the length of the silicon layer and the varying the area, cross sectional area of your silicon layer, you can vary your resistance, right? So this resistor value, depending upon your what is the circuit needs, you can realize by assigning a particular, by designing your particular length and particular cross sectional area of your that silicon layer, right? So uh, uh, So this is, so suppose you need a more area, since let me tell you that when you realize your chip, I mean the chip size is constrained. So you have to have a particular portions you have to put it the your registers on a particular chip area. Since area is constrained, so you cannot have any length of your silicon layer, right? So for that, typically in a VLSI technology, VLSI design, the registers are realized like this. So that is a zigzag fashion. You can put it. This is this way you can design it your layers so that you can increase your. Okay. So here you can take your A terminal. Here you can take your B terminal. So within a cross sectional, within a particular dimension area of your chip, you can realize your silicon layer to get a particular resistance value in your silicon material, in your chip, right? And if it is not also sufficient, you can have a stack of this resistance, and where you can have connected to each other. So I mean, so you just put this resistance material, and you put a silicon dioxide material above that. Again, you put some resistance, particular resistance material, this resistor material above that, and do the connection between these two layers. So people are going with the three-dimensional stack to realize a high value of the resistance, right? So here precisely you can control your resistance, but the problem is that it will take a much area if you go with the passive component, passive resistors. But in the other end, if you go with the active registers, the active registers, say for example, either you go with the say suppose you go with your MOSFETs. Okay, you go with your MOSFETs. So in the MOSFETs, either PMOS or NMOS, or you can take your NMOS or PMOS. So source and drain, source and gate. If it is a source, this is a drain, and this is your gate, and this is your gate, this is your drain and the source. If you look, I think VDD. So anyway, the source and gate is connected. Then source and drain is interchangeable in the MOSFET device and MOS and MOSFET device. So you in your convenient you take whether it is a source or drain, you can nominate it. Uh, so in this case, what is happening, like the if you go to the characteristics, like MOSFET characteristics, I mean, when gate and source is connected, so it will be act like a it will be it will operate at the in the region of the active regions, sorry, saturation region. And in the saturation region, if you look at ID, ID, ID equal to mu n COX, right? Mu n CX by W by L into how can into L into VGS minus VTHN square. Okay, so if you take that differentiate delta V and delta ID, you will get a R, and that R value you can get that that active component. Again, it depends upon your all these parameters. So you have to precisely consider, you cannot precisely can control by controlling your voltage. You can connect a gate and source. Also you can get that active if it is source and drain, by biasing with a particular voltage level, that is your gate voltage, you can control your current flow over here, source and drain. So accordingly you will get your resistivity here. So if you go to the three-dimensional, how it works, let me tell you. Let me go with the device. So suppose take an NMOS device, N plus N plus, right? So this is your say source and drain, and this is your gate potential. So if you are getting like say IV, if you go with the IV characteristics, I and V characteristics, so then what will happen if you draw the current? So whether you are here operating at a saturation region or you are operating at a linear regions. So if it is a linear regions, then if you, I mean, that what I schematic, if you go the source and drain, so take a terminal A and B or get potential by depending upon your VGS, right? Depending upon your get potential, you will get your particular. It will go to the this linear regions, and if you take the this characteristics V by I, then you will get your R. You will get your particular R, particular region. So depending upon the which region you are operating your at which region you are operating your MOSFETs. You can operate at a linear region and you can operate at a saturation regions. So saturation region, it is very sensitive because you will get some parabolic nature, but in a linear region it is a very linear. So if you operate at a linear region, then it will be a very non-sensitive resistor. You will get it. It is not sensitive, but the problem is that you need to have your particular gate voltage. So you need a voltage source, separate voltage source that will be connected to your gate, right? That will be connected to the gate, because circuit is operated a particular frequency, particular voltage level, say 3 volt or maybe 1.8 volt, like that. At a particular voltage your digital circuit will work out, but to attain your resistor or to operate your transistor at a particular voltage level, operate at a linear regions. So you have to give a particular voltage level within 0 to 3 volt or 0 to 1.8 volt, depending upon your voltage you require. So if you require any voltage between this operating voltage of your circuit, then you need another voltage source to be connected to the gate, so that this transistor will operate at a linear region, right? So that you will get a non-sensitive resistor. Okay, but if you connect this gate to source, so since source is connected either to the VDD and the ground, depending upon the PMOS and NMOS connections, so that you can there is no need to get connected any to have any other additional voltage source to be connected. The same operating voltage source can be used to realize your resistors. But the problem that if you get and source will be connected, then it will go to the verge of saturation regions. So if you look at the saturation region, verge of saturation region in this point, so it will be your bit curvature like. So any fluctuation in your voltage, any small fluctuation in your voltage, your resistor will be changed. So if your resistor will be changed, then your circuit performance will be changed. Okay, circuit performance will be changed. But yes, but you don't need a separate voltage source to be connected, right? So this is the difference between your passive uh, passive resistor and active resistor, which will be connected to your driver circuit depending upon your NMOS or PMOS inverter. Clear? Anybody doubt? Any somebody has a doubt on it?
No, sir.
Hello? Hello?
No, sir.
Hello? Who was asking?
Sir, I was
Hello? Hello?
sir,
आवाज
hello.
मैंने आई एम नॉट ऑडिबल एक्चुअली टू यू.
Sir, I was
व्हाट्स योर नेम?
asking.
नाम बता दो, पहले नाम बता दो.
Sir, my name is Akanksha.
हाँ, आवाज नहीं आ रहा है.
Akanksha.
आकांक्षा. ओके ओके. हाँ, योर मैंने आई एम नॉट ऑडिबल टू यू एक्चुअली. वॉइस इज फ्लक्चुएटिंग. हेलो?
Sir, I was asking the doubt. It's clear now.
Okay, great. So now let's move to the CMOS inverter. Okay. See, Akankya, let me tell you one thing. Here that let me clear. It will doubt to maybe to all people. But you see what is happening here. Whether it is a passive load register or active load registers, there is a always some current will flow this resistive or resistive passive load and passive load or active load, because this active load, if you look at this transistor is on, so there will be some current will flow on this resistor. If current will flow in a resistor, then there will be a always power dissipations. There will be a always power dissipations. Okay, so it may be, it could be a leakage, and obviously it will leakage because it is in a saturation region. So it will accelerate your leakage current. So there will be always a power consumptions will be there. Either it is a NMOS inverter or PMOS inverter with your active load or passive load. In all cases, there will be a continuous power leakage power consumption will be there. But to minimize this leakage power or this static power, you can say there is a device you can use, the inverter you can use, that is called your CMOS inverter. CMOS inverter. Here in CMOS inverter, we can say that we will use both complemented MOSFETs like PMOS and NMOS. The circuit topology is like this. Circuit topology is like this. You have your VDD and you will have your ground, and it is your PMOS and it is your NMOS, right? And you will get your input and you will get your output. Okay, you will get your input and you will get your output. The circuit operation is like that. Let me tell you operations. If you give the input 0, right? So this PMOS is becomes an on and NMOS becomes off, right? And when the then if it is on, then output will be tied to the 1. And if it is a input is 1, if input is 1, then the PMOS will go to the off and NMOS will go to the on state, right? And the output will be tied to the ground and you will get a logic 0. So when it is 0, you will get 1. When it is a input is 1, output is 0, 0. So it is a inverting nature. So this way you can realize your CMOS circuit. Okay, you can realize your CMOS inverter. This is the circuit topology for the CMOS inverter. Okay, so see here what is happening. If you look at that path VDD to the ground, VDD to the ground, right? There is a path here. One of the transistor is always off, depending upon your input, either 0 or 1. If it is 0, then NMOS is off. If it is input is 1, then PMOS is 1. So there is no direct connection. I mean, there is no path you will find from the VDD to the ground. Okay, VDD to the ground. So in this case, what will happen? The static power that is called a static power become, that is your VDD into drain current ID. Okay, so there is a VDD into ID. So what happens here? that since both transistors are one of the transistor is off always, either PMOS or NMOS depending on the input. So there is no drain current from VDD to the ground. So there is no current, there is no drain current from VDD to the ground. So ID becomes 0. So static power becomes 0. So that's why this CMOS inverter, CMOS circuit is said to be a low power circuit. The CMOS inverter, CMOS circuits are said to be a low power CMOS inverter. It is not a case of the only inverter. It is a case of the all CMOS circuits. So that's why it is called a low power. The CMOS circuits are said to be CMOS circuits are said to be low power. Said to be the low power. Okay. So so compared to your NMOS and the PMOS circuits also, it is a low power. Okay, obviously it is a much less compared to your bipolar junction transistors and the in terms of power. So let me introduce the. I didn't talk about the bipolar because bipolar inverter. Let me give a one circuit of the bipolar inverter. Let another topology that is called your bipolar inverter circuit. Bipolar inverter circuit. So you can take the one of the topology you can discuss at least to understand the beauty of your CMOS circuit. That will be better. So this is your VDD and this is your ground, and you have a resistors. I will take a NPN, and this is my input. This is my your output. Okay, so this is your bipolar inverter. You might have studied in previous semesters. So logic is that if it is a 0, so it becomes your off, right? The bipolar will be off, and output will tie to the VDD. You will provide a 1, and if it is a 1, then it will go to the saturation. I mean saturation region, so it becomes on. So you will get your logic 0. So this is the circuit topology, NPN based inverter circuit. So similarly you can have your PN where you can take this one and the register will have to bring down. So this way you can get your bipolar inverter circuit realizations. Okay, inverter circuit realizations. So if you either you go to the bipolar and MOSFET, and which one you will choose it. So if you have a qualitative analysis for the bipolar or MOSFETs, so you will see that qualitative analysis, qualitative comparison between bipolar, qualitative comparison so between bipolar, एक minute. Okay, so bipolar and MOSFET. Then if you look at area, compare the area. In case of qualitatively, bipolar will have a larger area, and MOSFET is a less area. Okay, and if you look at the speed, bipolar have a more speed, and MOSFET will have a less speed. Man, speed performance. If you look at the speed performance, bipolar will have a more speed performance, and MOSFET has have a less performance. And if you look at the power, that bipolar will consume a more power, and MOSFET will consume a less power. Okay, so this is the qualitative comparison between the bipolar and MOSFET circuit. So if you look at that, MOSFET has a two advantage. That is, it consumes the less area, and it consumes the less power. Obviously, speed is less compared to your bipolar. Because of these two advantages, MOSFETs and area and power. So MOSFET is preferable in most of the applications. And not only that, if you look at the cost. Okay, if you look at the cost, see, fabrication cost of the bipolar will have a more compared to your MOSFETs. So if you look at that cost in terms, I'm talking cost means that is a fabrication cost. Okay, fabrication cost. The fabrication cost of the bipolar transistor or bipolar circuit will be a more, and the fabrication cost will be have a less. The reason is that the steps to realize a bipolar transistor is more compared to your MOSFETs. When the steps of the fabrication steps will be increase, accordingly your fabrication cost will also increase. So here cost in the sense that fabrication cost. Fabrication cost increases due to the more steps involved on the fabrications to realize a bipolar device or bipolar transistor or bipolar circuits in silicon compared to your MOSFETs. So cost is more. So this is another advantage. Another advantage you will get your MOSFETs. Hence, MOSFET is preferable in most of the applications. Okay, so this is the conclusion that MOSFET is preferable in the most of the applications. So we will study the MOS based circuits in this lecture series. So then okay. So now next we will go with the before going to the next step, let's we will study the characteristics. Okay, no, then next we will go to the let's really compare. There is two way you can move it. One is that either you will go to the next step of the full custom design, or you can go with the characteristics of the CMOS inverter. Okay, characteristics of the CMOS inverter or CMOS circuit. So better we will go with the let's really complete the full custom design steps. Then we will come to the more circuits and more characteristic or to know the characteristics of the MOSFET MOSFET circuits. It could be inverter, NAND, NOR, or whatever the circuits you can realize what is their characteristics, how that characteristics will be used to study the performance of your overall circuit. Okay, that we will study. So before going to the study the detailed MOSFET circuits and their characteristics, let's me complete with having this knowledge. Let's will complete our design flow, so that we can start our lab works. So now in our next step, if you go to the next step, our circuit design, what is your next step? So after circuit design, right? Circuit design, we need a circuit simulation, right? Circuit simulation. In circuit simulation, circuit design or circuit simulation, circuit design we have studied, and circuit simulation by by hand, by manually, how 0 and 1, 1 and 0 is coming for the inverter we have studied. But in this case, you also can take the help of a tool simulator to see the waveforms of a inverter circuit, right? Circuit simulation you can do it. So circuit design and simulation we can start in the lab class. Maybe next week we will start this lab class. And so before going to that, we'll go to the next step. What is your next step, Akanksha? What is your next step? Narendra? Hello?
Yes, sir.
Who is Kate? Huh?
Layout or physical design, sir?
Very good. What is your name?
Prasant, sir.
Prashant, very good. So next step is your physical or layout or physical design. Layout and or physical design. Right. So see, before going to the layout and physical design, let me introduce something like this. So you need some intermediate steps, though it is not mandatory, but it is essential, I can say. Say for example, when you are building your building, say I will talk about civil point of view. When you are building your house, so before going to your structural design, right? So you need your a floor plan, right? You need to have your layout design, right? I mean, like to to go to your uh, uh, to go to your actual placement of your rooms, you need to exercise, because layout design means what? Layout or physical design means that you are giving the actual dimensions of your layers, right? Or if you go to the building site, means you are giving the actual dimensions of your rooms. Okay, actual dimensions of your rooms. So before going to that, like what we have to do, because you cannot give the actual dimensions, it may happen you have to reiterate many times. So before freezing, because you don't know like where you will place your bedroom, where you will place your dining hall, where to put your drawing hall, or kitchen room, toilets, all these things. So to do rather exercising the your placement of rooms with the actual size, right? So which will consumes a more time to more time to do the iterations. So before to avoid this time consumptions, so what people do by a in a particular civil term, they take the help of a expert that is called a draftsman. Draftsman, you might have heard about this expertise, that those are known as a draftsman. What they do, the draftsman, the job is that they will just reiterate, and they will play with the lines. They will play with the lines like this. They will play with the lines like this. They will put you know uh, 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 some they will, and they will put lines, and they will say that where should be a what room, dining hall, drawing hall, kitchen room, okay, study room, veranda, okay, staircase. Though they will, they will put just, they will stick, they will place with the sticks, and they will look at other environmental, aspects, or another term is called Vastu aspects. So those who believe on the Vastu, so they will look at, and they will take the directions, north face, south face, east face, roadside, backside. So everything they will look at, and they will just exercise in the stick diagrams, and which will be the appropriate to place to design your house, right? So accordingly they will get it. They will get the they will exercise using your lines, and they will say, okay, this is the proper placement of the various rooms. Once it is done, then what the this architect people, or the structural design people, particular structural design people, they will construct the pillars by giving the appropriate appropriate, they will place the appropriate pillars and foundation and pillars at a appropriate place. Okay, they will do accordingly, right? So similarly, so it will, what it does, it will help the structural design people to exercise or iterate more times, which will take a more time. Okay, it will consumes a more time. So draftsman helps to the structural engineer to reduce the time of the placement of their pillars and the structures. Okay, so that draftsman. So similarly, in a VLSI point of view, when before going to the actual layout design, or particular by placing the actual dimensions of the layer, we have to exercise another, like a draftsman, that is called a stick diagram. Stick diagram. So the stick diagram, it is like this. So, and they will put the we have to put the sticks only. So say for example, you will go with the CMOS inverter circuit, VDD, and ground, and I'm drawing it. So you will get your PMOS, and you will get your NMOS. This is your input, and say A, and this is your output, say Y. So this is the circuit. Before going to the layout, we will have our stick diagram for that. So to get your stick diagram, what do we do generally? The rule is that you have to have your 4 lines, that is your VDD, and another is your ground, and in between you will have your one, you have to put it your, that is called P plus diffusion stick. Okay, and you will have your N plus diffusion stick. Okay, so using this P plus and N plus, these 4 sticks you have to put it, and P plus diffusion stick will be used to realize a PMOS, and N plus diffusion stick, it is it is a stick, right? It is a stick. You have to draw a 4 sticks in the beginning. P VDD for the ground, and P plus diffusion, N plus diffusions. And another vertical line you have to put it. Vertical line you have put with, that is to get your poly layers. So poly layers, because this gate is realized your poly layer, so that is a that is called a poly stick. This is known as a poly. This is known as a poly stick. Okay, so when the P plus diffusion overlap with your poly stick, then you can get your one MOSFETs, that is your, here you will get a MOSFETs, that is called a PMOS. PMOS, you can, this overlapping between P plus and poly stick, you will realize your PMOS, and overlapping with the N plus diffusion with the poly stick, you will get your another say, I don't know, like which color I can take it. Okay, same thing. Say I will take red only. So you will get your NMOS device over here. So one side you will get your source, another side you will get the drain. Similarly, here also NMOS also you will get one side source, another side is drain. Now the source has to be connected to the VDD. So source will be connected to your VDD, and this source, take a source. This is drain. This is your drain. This is your source. So source has to be connected to say. If you put a cross mark, then that will be your connected. Okay, the two layers will be get connected. So this is connected ground, and drain of the PMOS and drain of the NMOS will be connected through these connections. So you can take your output here Y. Okay, you can take output your Y. Polystick, obviously this is the input, so this is you can connect it to the A. Okay, so depending upon the number of inputs, you have to put the vertical lines. So there is a rule that how many vertical lines you have to put it. That depending upon the inputs variables, you have to put your same number of the vertical lines. Okay, that will create a poly layer in your MOSFETs, either PMOS and NMOS. So if you look at this, your circuit, from the circuit it is obvious. The above it is a PMOS, ground, below one is a NMOS. So for that you have a P plus diffusion, P plus diffusion. You might have a question that why sir P plus diffusion and N plus diffusion. The reason is that if you look at PMOS is realized by the P plus diffusion, right, and the P plus diffusions, and the NMOS device can be realized using your N plus diffusion and N plus diffusions. And the current in PMOS is holes, right, holes, and in the NMOS the current carrier is your electrons. So that's why it is called a P plus diffusion stick, and this is we are using the N plus diffusion sticks. And so by overlapping your poly, you can get your channel region, and here also in NMOS overlapping your poly, you will get your channel regions. So that's why P plus and N plus diffusion is used, and overlapping with your overlapping with your poly stick, poly layer, or that is your poly stick in the terms of stick diagram. So here you will realize a one MOSFETs, PMOS type, and here you will get a NMOS device. So connections you can do by putting the cross line on that points. So cross means that is a connected. Okay, so this is about the stick diagram, stick diagram of your CMOS inverter. So we will study more stick diagram for the other circuits also. But to understand what is the stick diagram, this is the basics of your stick diagram. This is a thumb rule where you have to follow it. Okay. So any doubt till this point I can take out. Otherwise, you will end the meeting. You may go to the next class. Prashant, do you have any doubt?
No, sir.
Yes, you can start. You can study this from the both Pucknall or Wolf, or that is called a CMOS. That is Baker book. Okay, I think all of you downloaded that books, right? If you don't not downloaded, then I upload in the MS Team so that you can get access. So either way, if you are able to download, it's fine. If you are not able to download, I have that one, so I can put in the MS Team folder. You message me in WhatsApp whether I should do or you can get it. Okay. Shall we end the meeting? Prashant. Hello. Hello.
Yes, sir.
Okay, so let's really end the meeting. And if you have any doubts, then I can take up, otherwise we will end the meeting. Shall we end? I think you don't have a doubt. Of course, these are basics. So let's really end the meeting. We will meet on the next Tuesday morning.